We also observed earlier that if you intersect two planes, they've got to intersect, like if this is a plane and this is a plane, they got to intersect in a line, right? Unless they're parallel. So we should, given two equations of a plane, we should be able to come up with the equations of the line of intersection, and it will have to be done parametrically. So how do we do it? Well, in another life, you have been taught how to do this. You just might not have been taught that what you found were parametric equations of the line of intersection. So what we're going to do is we're going to treat this as a system of equations. Treat as a system of equations. Now, it's two equations but three unknowns, so you can't solve for a specific x, y, and z point of intersection, can you? But what you can do is you can get each coordinate in terms of one of the other coordinates. So you could get like x in terms of y and z in terms of y, or you get y in terms of x and z in terms of x. You can do that using elimination. And that's what we're going to do. So what variable actually would be easiest to eliminate here? So I'm going to solve using some sort of elimination. And when I say solve, what I really mean is put each variable in terms of one other variable. And be consistent. If you put x in terms of y, put z in terms of y also. In terms of one of the other variables. So everybody just said, oh, it'd be easiest to eliminate z, so let's add the equations together and eliminate z. Why not? Let's do that. Add them up, what do you get? 3x minus 3y equals 18. Oh, and that reduces. Divide everything by 3. What do you get? X minus y equals 6. Nice. So I'm going to put x in terms of y just because it's super duper easy. Just add y to both sides, and I get x equals y plus 6. Would you agree with that? So I put x in terms of y, which means I want to put z in terms of y. How do I do it? You plug back in. Yeah, it really is just like the elimination method. Once you get x, you plug whatever x is into one of the equations. Which one would be easiest to plug into? Top one. So I'm going to plug it in right here. Now, that's going to leave me with two variables, y and z, but then I can solve for z to get z in terms of y also. So you may not understand why I'm doing this yet, but hopefully you understand what I'm doing to get everything in terms of one variable, right? So if I plug in y plus 6, I get y, for the first equation, I get y plus 6 minus 2y plus 2z equals 3. Okay, so combine like terms. How many y's do you see? 1y minus 2y, negative y. Plus 2z equals, subtract 6 from both sides, negative 3. Okay, so we want to get z in terms of y. So what's that going to look like? 2z equals y minus 3, if I add y to both sides. Which means z would be 1/2 y minus 3/2. Does everybody believe that? Okay. So what you did call this in another class was a dependent system. Do you remember expressing the solution, the ordered triple solution, actually solutions because there's an infinite number of them, as x, y, z all in terms of one variable? Does that ring a bell? So x, what is x? X is y plus 6. Y is itself. Y is y. And z is 1/2 y minus 3/2. So what we're saying is this is a dependent system. You give me a y, and I'll give you an x. So you pick y. There's an infinite number of solutions here. You pick y, so you pick this. And I can give you an x and I can give you a corresponding z that corresponds to a solution. In other words, it'll be a point on the line of intersection between these two planes. Does that kind of jive with what you learned in the past? Yeah, and a lot of you won't remember because it's been so long, but in pre-calculus, you did this kind of stuff. So what does this represent? This represents the solution set. Well, okay, what is the solution set? The solution set is the line of intersection. We already know that two planes intersect in a line, right? So the solution set is the line of intersection, which means the solution set is x equals y plus 6, y equals y, and z equals 1/2 y minus 3/2. These are the parametric equations of that line of intersection. Now, usually we set y equal to something like t. We call t the parameter. So if we say let y equal, say, t, then it becomes x equals t plus 6 or 6 plus t. You get y equals t, and z equals, I'm going to put the constant first, so negative 3/2 plus 1/2 t. And so these are the parametric equations of a line. And in this case, they're the parametric equations of the line of intersection. So your instructor back in pre-calculus or college algebra might not have told you when you solved this dependent system that that's what you were finding, but that's what you were finding. You were finding the parametric equations of the line in space, and that line was the line of intersection.